Hello everybody, my name is Elnur Shahbalayev. I'm from Petroleum Engineering Department and this lab will be about the impact of a jet, which is Fluid Mechanics Lab. So the table of content is introduction and theory, objectives and methodology, experimental setup, results and discussion and conclusion. So introduction and theory. Water turbines are widely used throughout the world to generate power. In the type of water turbine referred as a Pelton wheel, one or more water jets are directed tangentially onto the vanes or buckets that are fastened to the rim of the turbine disc. The impact of the water on the vanes generates a torque on the wheel, which causing it to rotate and develop power. Also, the concept is essentially simple. Such turbines can generate considerable output at high efficiency. Powers in excess of 100 megawatts and hydraulic efficiencies greater than 95% are not uncommon, which is very good number. And it may be noted that the Pelton wheel is best suited to conditions where the available head of water is great and the flow rate is comparatively small. You can think of it as water dams where the height of the water is quite big, which is the water head, but the flow rate is comparatively small because it stops the water and the speed almost decreases to zero. And to predict the output of a Pelton wheel and to determine its optimum rotational speed, we need to understand how the deflection of the jet generates a force on the buckets and how the force is related to the rate of momentum flow in a jet. In this experiment, we are going to measure the force generated by a jet of water striking a flat plate or a hemispherical cup and compare the results in the computed momentum flow rate in the jet. So as you can see, we will have two kinds of results. One of them is a flat plate, the other one is hemispherical cup. So for the methodology, the apparatus is first leveled and lever brought to the balanced position. Then the water is admitted through the bench supply valve and flow rate is increased to the maximum. The force on the wing displaces the lever, which is then restored to its balanced position by sliding the jockey weight along the lever. So the mass of flow rate is established by collection of water over a timed interval, and the condition of the balance is thereby found without touching the lever, which is much easier than finding the point of balance by sliding the jockey weight. So to sum up, the experiment should be run twice, one of them with the flat plate, the other one with the hemispherical cup. So this is our experimental setup. We have spring supporting lever, fulcrum, nozzle, where the water goes out, the vane and the jet, trolley, and we have water coming from the supply to the nozzle, and it goes to the waiting tank. Okay, so we are given the diameter of the nozzle, and from the diameter we can find the area using the PD square over 4 formula, and the height of the vane above nozzle tip is also given, and distance from the center of vane to pivot of lever is also given, and all this is given. So using these numbers we can find the F, which is the force, and also these different numbers can also be found using our experiment. And as you can see, there are two results: the result for the flat plate and the result for the hemispherical cup. Actually this is a bit hard to understand from here what these numbers showing us. Then let's graph them. So after graphing them, we can see that the force on the vane F is proportional in both of them. However, the slope is different. So while the rate of momentum flow in jet is almost the same. So as you can see, flat plate has a lower slope while the hemispherical cup has a higher slope. What does it mean? It means that if we use a flat plate, uh, while having the same rate of momentum flow in a jet, we will have less force generated. If less force is generated, it means that we will can generate less electricity. So logically, if the hemispherical cup will produce almost double, two times of the energy as much as the flat plate. So as we can see here, just a bit of the shape difference can make a lot of difference. So we need to consider this in general life and applications of this law. So it is clear that the force produced on each vane is proportional to the momentum, as I said before. For the flat plate, the slope was 0.97 as compared to the ideal value, which is 1. The discrepancy of possibly due to systematic experimental errors, such as small error in the measured value of nozzle diameter. A further possibility lies in the behavior of the jet after striking the vane. It forms a radial sheet which impinges on the inner wall of the surrounding cylinder, then divides some of the water flowing down the cylinder wall and the rest flowing upwards like that. So also the visibility impaired by the spray which is generated. It does seem that some water falls on top of the side of the vane. This will have effect on producing small momentum force in the downwards, which will decrease the efficiency, so reducing the net upward force on the vane. But for the hemispherical cup, the slope was 1.92, so that the force is equal to 1.92 multiplied by J. So the maximum possible force is shown to be 2J, which occurs when the jet is deflected through 180 degree like that. So one complete, almost not complete, one half complete cycle. So the ratio between measured force and the theoretical maximum may be regarded as the efficiency of the vane, which is 0.96 in this case, and will always be less than 1 because there is always less losses in real world, and the conditions without loss is only possible in ideal conditions, and ideal conditions are not possible in the real world situations. Actually, this was all about our experiment. Thank you for your time, and thank you for watching. Have a good day.